Society challenges. So I am Nicola D'Ascenso. I come from the University of Science and Technology of China in Hefei, and from the Istituto Neurologico Mediterraneo in Molise, which exists, is in Italy, is a small region of Italy, but and with a great technological expertise in, so actually, apart joking, so a main background in, my background is in positron emission tomography and application of physics to medicine and also agronomy.
Good afternoon, everybody. I am Mara Bruzzi. I am from the University of Florence and the INFN Florence section in Italy. My research field is mainly on the development of semiconductor materials and devices for applications in medical physics and environmental safeguard. So we should start now this session. So I wish to introduce you the first speaker, Professor Simon Jolly, who is coming from a University of College of London and will speak about FLASH-radiotherapy, new paradigms, new challenges.
Thank you. So welcome everyone. Thank you first of all to the organisers for the opportunity to talk to you about what is a very interesting field, something that's happening that may transform radiotherapy, transform how we treat patients. So because this is a physics conference and I'm also a physicist, I should do the usual thing and starting off by talking about things that I don't understand, which is the medicine and the medical treatment. I'm hoping that most people in the room have some idea about radiotherapy and about how you treat with ionizing radiation, but the essential principle is that you're trying to bombard cancerous tissue with some kind of ionizing radiation that causes double strand breaks in DNA. That's the same actually if you're treating with chemotherapy. You're trying to break the DNA strands of those replicating cancer cells, and in doing so, as they fall apart, then the cell recognizes that even in its cancerous state, it's no longer able to replicate and perform its cancerous function effectively. And in that case, the cell then self-destructs and dies. So the more radiation dose you deliver to the cancerous cells, the more effectively you're going to create those double strand breaks, the more highly clustered you're doing that radiation deposition, the more highly clustered that dose is being deposited. So with hadrons as opposed to X-rays or electrons, the more tightly clustered those double strand breaks are going to be and the more damage you do, which is why we use different radiation species, but we will talk about that as we go along. The conventional way of treating with radiotherapy is with X-rays with anywhere between 6 and 18 MeV electrons hitting a target. They're then produced by a radiotherapy gantry, so you have an X-ray beam that comes from normally a tungsten target, and that entire gantry then revolves around the patient through 360 degrees. And you have different methods for shaping that beam so that the size of the beam is then shaped to the tumor as it rotates around the patient. The issue that you have with X-rays is they pass right the way through the body, so you need to treat from all 360 degrees in order to do the damage where you want it rather than close to the skin, which is the peak point of dose deposition. Anybody who works in high energy physics will hopefully have heard of something called the Bragg peak. So when we move from using X-rays to using protons to treat, the reason we do is thanks to beta block, we've got this very tight region of peak dose distribution. So because of the mass of protons, we end up with a much larger peak at the end of range and also a fixed range. So protons will go a known distance for a given energy. As long as you know the absorption of the material that proton is passing through, you know how far it's going to travel, you know that it's going to deposit its dose within a fairly tight volume, and the dose deposition afterwards is going to be essentially zero. You do have some neutron production afterwards, but the dose deposition is much, much lower. You get an even tighter dose distribution the heavier you go, which is why we treat with carbon. something I won't have time to discuss, unfortunately, with carbon, you also get enhanced immune response. The immune system seems to wake up when you treat with carbon and go, I need to remove those cancerous cells as well. That's an area that's under study. The disadvantage with carbon is because it's a nucleus as opposed to a single particle, you do get fractionation in the nucleus, so you end up with this larger tail, the fragmentation tail on carbon compared to protons. For those who have come across VHEE, so very high energy electron radiotherapy, again, that's an area that's under exploration. Electrons behave essentially like photons when it comes to treatment. You're talking about short-range electron showers in both modalities that do the damage. So it's quite different between hadrons and the light electromagnetic particles. You can steer electrons, which you can't do with photons, but other than that, the dose deposition is quite spread out. You don't get the Bragg peak with electrons. To prove that we know what we're doing, this is what an image of a Bragg peak looks like. So the beam is coming in here, I think, what is this, 140, 150 MeV? 110, okay. So brighter and brighter and brighter, this is a block of plastic scintillator, and then stop, and that hard stop, that's the Bragg peak. And within a few millimeters, that's where you get the peak in your dose distribution. And when you look at the difference between IMRT, so intensity modulated radiotherapy, so this is X-rays, this is protons, the important difference is the amount of dose that you're getting outside the region that you're trying to treat in. So this is your isodose line, that's where you're trying to deliver your dose. Between protons and photons, you deliver exactly the same amount of dose to the tumor. You need to deliver enough dose that the tumor is going to die after 20 or 30 different, what we call fractions, so treatments, one per day over the course of a month. The key thing is the low dose bath that you get with X-rays is much higher than it is with photons, and that's, so with protons, and that's why we treat with protons. So what am I talking to you today that's actually interesting? The important thing when minimizing the dose to healthy tissue is what's known as the TCP-NTCP ratio. So TCP is tumor control probability. You need to deliver enough dose to the tumor that the tumor does not continue growing and spreading, but then shrinks and dies and the patient goes into remission. But the more dose you deliver, the higher the likelihood of normal tissue complication probability. So you're trying to balance out those ratios. And really, you pick a point on this TCP-NTCP curve where you're maximizing the tumor killing probability and minimizing the damage to healthy tissue. What's been discovered in the last decade is that if you treat in very short amount of time, so rather than delivering that continuous 360-degree dose in a few minutes, you deliver it in 100 milliseconds. For some reason, the healthy tissue survives much more effectively with higher doses than it does with normal doses delivered over those long time periods. And what that means is you see healthy tissue sparing for the same dose that you would see healthy tissue damage. And in medical terms, that means that you are changing your TCP-NTCP ratio. You're making life better for yourself, but the challenge is that you have to deliver in these very short times. It seems like 100 milliseconds for your entire dose delivery as opposed to 2 to 5 minutes is the key point at which you start seeing this immense benefit of healthy tissue sparing. What that means is treating that fast is challenging. And that's the main thrust of what I want to talk to you about. Something to keep in mind about this is that the flash effect doesn't change the damage that you do to the tumor. The key thing is it's the damage to the healthy tissue. So if you see people talk about flash treatment and they're delivering dose to healthy tissue that otherwise you wouldn't, you're not getting any benefit of flash. You're trying to minimize the effect to healthy tissue by treating it these very short times. So one of the leaders in the field, a guy called Jean Bourhy, who's at, I think he's at the hospital in Vaudois in Switzerland, This is a patient who was treated who had a lymphoma, so close to the cutaneous lymphoma, so it's in the skin. And they treated, this is with x-rays, so again with these very fast treatments, and you see really remarkable remission of the tumor. So the healthy tissue sparing was very surprising. And it's something that's replicated in animal experiments. So as far as I know, this is the only clinical experiment that's ever been done. You have 3 types of particle at present that are really being looked into for FLASH. So each one has its advantages and disadvantages. The treatment that I just showed you was done with photons, so the advantage of photons is that we've been treating for a long time. The treatment modality is very well established. The only problem is if you're trying to treat in such short bursts, you normally melt that tungsten target. You're dumping so many electrons in a short time that you can't produce your photons fast enough. So how you actually produce those X-rays is going to be quite challenging. And then how we do how we actually treat, given that we're used to treating over a couple of minutes with these continuous 360-degree sweeps, it may well be that you will need novel linac designs where you've got multiple linacs all shooting from different directions to give you that burst, that bang in one go. With electrons, you have similar but different problems. High current electron linacs are already available. I mean, you can easily get milliamps of current out of an electron linac. There are no clinical electron machines at all, primarily because photons are easier. You need bigger machines to get the penetration depth for electrons. You don't have a Bragg peak, so they haven't really been looked into except for very shallow treatment. And there aren't even any preclinical systems. So there's going to be quite a lot of R&D that's needed before electron systems come into being. With protons, you've got the advantage of the Bragg peak, and there are lots of companies that produce commercial proton therapy systems that are very interested in FLASH, that are already working on those kind of systems. Unfortunately, they don't have the current that we need, so those systems will have to be upgraded. You also have the real problem of how you go from scanning in a few minutes to scanning, you go to scanning in 100 milliseconds, so I'll talk about that in a minute. And most important for this conference, we need new technology in the dosimetry. So these numbers are not for you to take in, but just to give you a sense of the challenge with spot scanning, that the normal dwell time per spot, which is about 2 millimeters apart, so you're scanning over at a single energy, 2 millimeter spacing, is somewhere between 5 and 20 milliseconds. So now you need to go from delivering one spot in about 5 milliseconds to delivering every single spot somewhere close to 100,000 spots in 100 milliseconds. So the requirements for your magnet scanning go way, way up. And if you want to scan an individual spot in something like 200 to 400 nanoseconds, which is how it has to scale up, then 5 to 10 meters per millisecond is how quickly your magnets need to scan. And the PSI gantry 3, I think it is, the max speed is 2 centimeters per millisecond, so there's a lot of work to do. The other problem that we have is in dosimetry. Now, the way that treatment is currently done is that you trickle fill, so you're adding charge to each spot and monitoring as you're going along. So you're not delivering all of that proton charge to each individual spot in one go. You're sort of adding a little bit and 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 just adding up as you go along. So just a little bit of charge and a little bit of charge and a little bit of charge. And at the point at which you know you've delivered enough charge to that spot, you then stop. You've got tens of milliseconds in which to measure it. Now, when it comes to FLASH, you're sort of doing it a little bit more like this, and you need to monitor at that speed. So if you're thinking 200 to 400 nanoseconds per spot, now you have a challenge in dosimetry. Now you have something that is significantly more challenging than it's previously been. So we need new technology. We need new tools. Ionization chambers are not fast enough to respond at that speed. And the other problem that we have is that that's a critical part of the patient safety system. If we are delivering so quickly, we also need to be able to shut the beam off that quickly, because if you overdose, then the patient's going to have significantly more dose in one area, significantly less dose in another, and that's a critical safety problem. So it will require new thinking about how we treat. What we also need are new quality assurance tools, because we don't have any way of measuring how effective the beam is, how much dose we're delivering, to confirm it independently, and that means we'll also need new technology. So the project that we've been working on at UCL is to develop some new quality assurance tools for proton beam therapy. So I want to invite Saad Sheikh to come up and just tell us a little bit more about the Quark project.
Thank you, Simon. Okay, yeah, so hello everyone, my name is Saad. I'm going to talk to you a little bit about a detector that could feasibly scale up to the FLASH QA requirement. So the detector we're developing in the proton beam therapy group at UCL is called the Quark. It is a quality assurance range calorimeter for proton therapy. Now, as Simon's alluded to, the proton range is an extremely important parameter when optimizing patient safety. You really need to understand this parameter well so that you know where you're delivering most of your dose. And so the way our but the problem is, practically in a clinic, each morning before you treat a patient, you're spending time doing this QA, and you have to do this every day, monthly, and also yearly. And the time you spend doing this is time that could be spent treating patients. So rather than spending an hour on your QA, we hope to maybe reduce that down to a few minutes. So our detector, simply put, is a series of optically isolated polystyrene scintillator sheets, each individually coupled to a photodiode. And I'm not going to go fully into the details of we do this. There's a poster that I'll be presenting after this. But the short of it is that if you measure the light output of each scintillator sheet, you can then reconstruct a depth light curve, and then we are able to then reconstruct a depth dose curve. And from this, we're able to extract the proton range. And so the key benefits of a detector like this is that plastic scintillator is inexpensive and water equivalent, and the latter is quite an important point to highlight, because the range that you measure has to be in water. It's a water equivalent range, simply because water is a good proxy for human tissue. And the key factor for maintaining our speed is that we can reconstruct the range with a single beam delivery. So I'll quickly show you some results. We did a beam test back last year at the new Proton Therapy Center at University College London Hospital, and we tested energies between 70 and 110 MeV. And what we found is that despite poor signal-to-noise ratio, some other problems, we were able to reconstruct the range quite well, within 0.5 millimeter. And the precision we want to reach down is to about 0.1 mil. And while we were only using 1% of our total headroom, we were able to also establish real-time range reconstruction, 6 kilohertz with 40 hertz range fitting. But just to bring this back onto Flash very quickly, as Simon has said, there are many technical challenges for realizing Flash in the clinic, and there is no real clinical guideline. Current estimates are about 40 gray per second. And this is about 1,000 times greater than what you currently offer at a proton beam clinic. And as Simon said, the current detectors used for QA, they just fail at this level. However, scintillation light does scale linearly with dose rate. And as we established from only using 1% of our total headroom with normal beams, and a rough calculation giving a 200 factor increase in light, this is a detector that could feasibly scale up to FLASH QA levels, something that no other detector in the field can really claim. And with that, I will hand back off to Simon.
Thank you, Saad. So just to conclude, there is great promise in treating with FLASH, and there are a lot of different sensors that are very interested in how we could deliver so quickly, but it is challenging, particularly with protons. There are the biological reasons about why this flash effect occurs. It seems to be related to oxygen depletion. So the tumor itself is hypoxic, whereas healthy tissue has a full oxygen supply. So if you're in a depleted oxygen environment, it seems like you can still do the damage in these short times that you don't do with the longer treatment times. We need to think about how we deliver the treatment in new ways. Do we still trickle fill but very, very fast, or do we know a priori how quickly the treatment is going to be done, so we know exactly how many protons that we're going to deliver? That's a very different way of thinking about it. We need new dosimetry tools. We need new monitoring tools. So for those of you in the field developing new detectors, please, if you have some interest, this may be a fruitful area for investigation. We're looking at scintillators. There may be other technologies, ways of mitigating that fall-off that you see in the ion recombination speed for dosimeters, which are the gold standard. And finally, my thanks to Andrea Schuler, who's the head of the UHD Pulse project, who gave me a number of the slides that you see here, and is coordinating the dosimetry effort in Europe. Thank you.
Thank you very much, Simon, for this very nice talk, quite stimulating and research. Yes, there is a question. First here and then another one there.
Thank you very much. Very nice talk. So I understand that you're talking about a detector that's monitoring the beam. What do you do to...
Sorry, a detector that's...
monitoring the beam.
Yes.
What do you do to monitor the patient?
What are you looking for from the patient? No, that's my question. What do you want to know?
Whether you are striking the tumor where you want it to be struck.
You don't. Yeah. So there are two.
Talk to me.
There are two possibilities that are under development. One of which is prompt gamma emission. So you're looking at the prompt gammas that get emitted from the excitation as you deposit those photons. The advantage of prompt gamma is that you get a stronger gamma signal in, it's give or take proportional to dose, but the signal is so poor that it's very difficult to localize where you're depositing that dose. The other option under investigation is with PET, so you're looking at the production of PET emitters. You get a much higher signal, but you're getting most of that signal at higher energy. The lower the energy that you go, the less the PET signal, which means that your Bragg peak is here and your signal is over here. So beyond that, there is no method of doing in vivo dose monitoring. The other method that is also under investigation is ion acoustic imaging. So you're looking at the ultrasound emissions, but that needs a highly pulsed beam. So you've got very short pulse of protons, and then a gap, and then you look at the acoustic emissions that come out. But as far as clinical treatment, no, there is no way of monitoring in vivo where the dose is going. You give it your best guess. You do your planning, and then you line up the patient based on their bony anatomy from a CT scan, and then you say, I think the dose is going in the right place. And I am sure it's one of the reasons why you see range errors from protons, why in some situations like prostate, you get worse treatment with protons than you do with photons. When you say, no, protons should be better, it's because you don't know exactly where your dose is going.
Yes, Fabio Sauli here. I've been working along similar lines years ago with proton beams. The problem that appeared is, for the same reason that you destroy the cells in the patient at these high dose rates, you also destroy the scintillators very quickly, at the same rate, in fact. So ideally, one should do the monitoring of the range at lower intensities. Unfortunately, at least with protons, there was no insurance that if you reduce the intensity using magnets, you get the same profile. So my suggestion is that you think of a different type of monitor, for example, gaseous devices that are not so easily damaged, or in any case, you can easily replace. With scintillators, I don't think you are going to make it.
You've got one advantage. So with gaseous scintillators, I know they've done some work at PSI looking at the scintillation emission from gas volumes. The thing to bear in mind with flash is that the total dose is the same. So the speed at which a scintillator degrades is proportional to the total dose, not the instantaneous dose. So if you're delivering exactly the same number of protons but in a much shorter amount of time, you have to collect a much higher light output and your detector has to respond faster, but your total dose is the same. So that's where I...
At this intensity, you see the light with your eyes. You don't need any kind of amplifier or detector. So
Yeah, I mean, you'd be able to see it in daylight, I
I'm
suspect.
suggesting that scintillators are not the proper option.
Well, scintillators aren't used because the light output varies. So if you want to do an absolute dose measurement with scintillators, they're not appropriate unless you have some way of calibrating exactly your light output to dose, and I don't know of a way of doing that. But the problem we have with anything that's based upon a dosimetric measurement is just too slow. So yeah, we have to look at other ways. If anybody wants to ask questions afterwards, please come and find Saad. We got time for one?
Maybe I'm sorry, we should go on. And we thank you for the very nice discussion. Maybe we can go forward with the next talk.
The next talk is from Giulio Saracino from the INFN. He is going to speak to us about a new cylindrical detector for borehole muon radiography. So we plug him in. Okay, good.
It's fine.
Fine, it works. So thank you, Giulio.
Cursor. Where is
the cursor is over there.
This is the laser. Perfect. Good afternoon to everybody. I'm very glad to present here in this wonderful conference this new cylindrical detector for borehole application of muon radiography. So probably most of you know about muon radiography because of its application in archaeology. In particular, some years ago, a big void was discovered in the Great Pyramid of Giza, but there are many other applications of this technology in volcanology, in geology prospection. For example, you can look at a poster in the poster session. Also, there are applications in the scanning of nuclear waste or nuclear plants, monitoring, and also control for blast furnace processes. So many applications, and how it works, of course, is based on the capability of muons to cross a lot of big thickness of rocks. And basically, there are two ways to make muon radiography or muon tomography. One is by absorption, transmission, let's say. In this case, the physical phenomenon that you use is the energy loss inside the matter that depends on the opacity, that is the product of density, mass density, and thickness. In this case, you measure the muon flux attenuation with one detector. So you need just a single tractor detector that measures the direction of muons, the quantity of muons. So from that information, you can measure the opacity. So in this way is similar in some sense to standard X-ray radiography. The other technology, the other way to use muons is by scattering. In that case, you need two detectors, one upstream, the other downstream, and you measure the scattering of muons. In that case, it's a Coulombian multiple scattering that you use. But this kind needs two detectors, two trackers, one upstream, one downstream, so it's not used in geophysics, for example. And where to place the detector, where the detector position. So you can place in a side position, for example, on the flank of a volcano, and then in that case you measure the almost horizontal flux of the muons. Or if you have a gallery, sometimes you have a gallery place where you can carry a standard, let's say, large detector, you place there, and you can measure the vertical flux of muons. Or in many cases, it should be very important to have the possibility to have a borehole, to drill a borehole, to place a detector inside the borehole, and to inspect all the volume around the borehole. So I will talk of this last possibility. In the past, have been developed and are developed many different borehole detectors, for example, for detecting ores in mines or in archaeology or for the monitoring of CO2. And basically there are proposed two kinds of detector till now. A planar geometry that is very simple to implement, but of course it doesn't optimize the geometrical acceptance of the cylinder. The other way, already in 2017, INFN was developed a beautiful cylindrical detector based on scintillators bars and scintillators fibers in helix configuration. It was used for archaeological application. It was 14 centimeter diameter. This is a very compact and good acceptance, but of course the number of channels start to increase very much with the diameter. So what we propose to have an arc-shaped scintillator and bars to have a two cylindrical coordinates system way to measure. So a layer of arcs measure the z coordinate, while bars along that are parallel to the axis measure the phi coordinate, the planar angular coordinate. So if you have two half cylinder, for example, in this way, you can measure the track. So this is the basic idea. And so we used these, we designed, we made some compromise between number of channels, surface, diameter of the borehole. So we designed a detector that can be used in 25 centimeter diameter borehole, and this is more or less 20 centimeter the diameter of the sensitive part. That is made of 64 layers, each layer of arcs. That each layer has 4 arcs, and then there are 64 bars. So in the total, we have 3,020 elements, scintillating elements. We performed several Gen4 simulation, and for example, here you see that we expected with this geometry we expect an angular resolution of 0.7 degrees in azimuth and 3 degrees in zenith. Here you can see a simulation of a cavity, a spherical cavity in the underground, and you place the detector inside this borehole. And for example, the red one is the excess of ions in the direction of that cross the cavity. So also we performed several laboratory tests in order to understand how to measure the light transmission along these scintillators, and at the end, to simplify the design, we just used no wrapping at all, and we decided not to use wavelength shifting fibers, and so the scintillators are suspended in air, producing a good transmission by internal reflection. Then we couple directly the CPM to the surface of the scintillators. You see here, for example, that we collect more than 20 photoelectrons from this side, but we use 2 Silicon PhotoMultipliers, and the same at the half center of this 1 meter long scintillator, we collect more than 20 photoelectrons that are enough for have good tracking efficiency. And this is the way we position the scintillator. So we produce these shells with 3D printing, ABS, where we have these guides to insert arcs. You can see here that we have some spacer in order to have this layer of air around the scintillators. In this way, we have, of course, optical insulation between all the scintillators, but we also have a controlled surface of air in order to have good transmission of the light. And this is top view. With 4 of these, you assemble it mechanically and have a half cylinder. The CPM were placed on a small PCB with a connector. You can see some picture about the positioning of this to the scintillator. And here is the 6 front-end boards for each half cylinder. Then you have 2 half cylinder, and then you assemble it on a steel base, and then you cover with a watertight shell of stainless steel. Then you have the power supply and the Ethernet connector. The front-end electronic was the same that we developed for the Murray and Muraves experience. So I will not give details now, but anyways, based on the EasyRock ASIC, we control 12 of these boards with a master board, and we have a Raspberry Pi and the Arduino for the connection and the temperature control. Here is a plateau from laboratory. So you see that changing, so increasing the threshold of the discriminator, you start to have accidental coincidence, then we increase and you have a very stable long plateau for cosmic. Here also we tested for long periods the stability of the trigger, it's quite stable, and also the comparison between the measured flux and the expected by a simulation are in good agreement. And then we tested in a cavity, in a set of cavity, where in particular we are using, let's say, our laboratory, natural laboratory in Naples, that is Monte Echia, or also probably some of you know as a Pizzo Falcone, or Monte Dio. Anyway, is a very ancient settlement of Greek, and was the ancient Parthenope, the first village from Greeks in the 80th century before Christ. And inside there are many, many cavities. You can see some drawing here. We placed the detector in several places to make several measurements. You can see here, for example, in horizontal and also in vertical. And first of all, we noticed that if you measure the total energy of the track, so you sum all the energy of the cluster that forms the tracks, you see that here, no, this is open sky, so upstairs, and then in underground you have this peak, and we think that is a gamma activity from the natural radioactivity of the rock, because of course this is tough, and there are many daughters of these old life isotopes. So anyway, this is not a problem because most of them are not able to produce a trigger, and the one that are able to produce a trigger can be cut away by this, no? Because the energy is much less than the one produced by immunes. So we make this cut, and we can reject this natural background. And you can see that some years ago we performed some measurement with the Murray detector that was developed for the Vesuvius, and we place this detector and make this picture. This yellow are the signal excess of muons, let's say, that correspond to known. This is the place where we play with the position of the detector. So there are many cavities that are intercepted by the acceptance of the detector. So this is a large, no? This is a 1 meter square detector of a surface, while this is our new detector. You see that there is a good agreement between the two measurements. And so I go to conclusions. So myography is an expanding technology. Many applications are around, and in particular, borrow detectors I think are an interesting tool for geophysical applications. And we optimize the acceptance of the detector using this arc-shaped scintillator, and this Borel detector was also patented, and we obtained good results in cavity detection in this laboratory underground in Naples, and also we are planning a real Borel measurement, placing the detector inside the Borel to conclude our test campaign. Thanks to everybody.
Thank you very much, Giulio. So I think there is already a question.
Did you determine the cavities, or did you find cavities that are there in your measurements, or not? I'm not completely clear. You put it in cavities, I know, but there were other cavities that...
No, this is, okay, maybe the drawing is very small. These blue are all cavities. You see the blue. So we put the detector here, and where there is this is no cavity, is where you see yellow. This is a elevation angle.
Did you measure in one position or in
This
several?
is just in this position. Then we place also another position. But this is, in particular, a comparison. We already published several papers with these results with this large detector. And so the first thing was to compare the new detector that is much simpler. Here there are 3 planes, it's large. We didn't see any radioactivity, for example, here, because with 3 planes we don't. And so you see that this shape, for example, is a room that was on the top of a detector. And then this is the elevation angle. That means 90 degree, 18 degree in the top. So we see the answer, yes, of course we see the cavities, fortunately.
We have time, I think, for at least one more question. Yeah, over there.
I heard that some people are interested to use this technology in the oil industry, to have boreholes and look for some abundant oil which has slightly different thickness, in metal thickness. So are you aware of this, or are you collaborating, or are some plans to use this there?
To be honest, nobody, to my knowledge, is using this technology for oil, because it's really, typically you have really go very deep in the underground. But what is, and there are several spin-off now working in the world, in Canada, for example, they are interested in ore mines.
Ore,
yes,
yeah.
This is used, that you can find very interesting article published, and there are at least 2 or 3 companies that are interested in this. In that case, they use, of course, 15 centimeter detector, are much smaller because typically they go to 300, 400, 500 meters. So they need to have small. This is for, let's say, 50 meters, maximum 70 meter so it's for detecting cavities for many geological applications.
If you go too deep, you get rid of the muons at some point, right?
No, if you go deeper, we can, but of course, since it's larger, the cost is, of course, this is a better acceptance, and over 15, it's much better, but the problem is to drill a 15 centimeter diameter or a 25 centimeter. There is a cost that is, of course.
Okay, thank you.
We have time maybe for a quick curiosity, if something there. Maybe I have a very, is there? No. Maybe I have a very quick one. So because coming from China, immediately I see an immediate application to security, right? So if I think to the Shanghai harbor, of course this technology can be used directly for the mass security systems for all the containers which are coming, yeah? Because you have the muon scattering.
This is not from scattering. Of course, there are several industry also that in this case, we are for security, not for, let's say, for the uranium or other.
Yeah, right.
They're using this in yes, it's the other technology that I showed at the beginning with 2 detectors. So it's not for Borel application. Let's say.
Exactly. Yeah. So, but are you thinking maybe to extend
no.
Your technology to that?
No, it's enough. There is already a lot of work for this. No, there is a lot of work to do with this, and we are happy. Of course, but also in Italy we have people that is involved in this. Yes, right? In multiple scattering from several years. Of course, I didn't have time to show this. This is a little bit. My talk was focused more on these activities that are close to my scientific.
Okay, great. So
thank you.
Thank you very much.
You're welcome.
The speaker again. And now we will have a small presentation about all what you find in the poster session while Mara gets connected. Yeah. So we will give you an overview of the poster session so that later, maybe during the coffee break, you can have a look to the 20 posters which belong to this session. Yeah.
It's okay. Should I? Okay. This is just to go on. Okay. So now I take this. Okay. I will present, we had 20 contributions in the poster session. So the idea is that we divided into main classes, as actually this poster session is about application to life sciences and other societal challenges. So I will present the first group of posters. Okay, sorry. I will present the first group of activities that are more inherent to life science. And in particular, the idea is to work out the ideas and technologies coming from nuclear and particle physics to the benefit of medicine. And kind of, let's say, research activity can be grouped into 3 main classes within this section, which is increasing accuracy in external and internal radiotherapy, and novel implant technologies, and improving cancer diagnostic tools. Considering the first class, the first paper I want to present you is actually the one we already saw in the first presentation. It will be presented by Saad Shaikh, that already told us a few details about this interesting activity, which is the idea to build up a real-time range measurements through a detector, which is made of a stack of water equivalent scintillators. So I will skip maybe this and go directly to the second that I want to present now, which is a work made by Moglioni et al., which is wanted to exploit the use of in-beam PET directly used inside for particle therapy systems, just to detect the morphological changes in proton therapy that can give a source of range uncertainty. So in this work, sorry, I have some problems here. Here you see the PET plants and the system that is used for in vivo range monitoring, and then the purpose is to, in this particular work, is to assess the sensitivity of this system in detecting the anatomical changes. So the patient treatment planning that is shown here is compared with the one measured in vivo, and you can see here the green line that is giving the target volume to be irradiated, and in arrow you see the morphological changes here. And then the deviations are calculated using different kind of method as the most likely shift, and here it is presented the underestimation and overestimation by this method that are coming from this analysis. I shifted to the third poster, which is concerning the development of a reconfigurable detector for measuring the spatial distribution of radiation dose. Here, the idea is to develop a novel detection system which is dedicated, to personalized radiation therapy planning. The idea is to use a set of 3D printed tissue equivalent material, like the detectors in here, about 1 centimeter size each, and then to use a set of slices to be used through a machine learning technique to analyze back the medical imaging and then reconfigure and generate a detector geometry which is more suitable for the particular configuration of a patient. Coming to another technology which is concerning radiotherapy, but in this case internal radiotherapy, meaning brachytherapy. This is a project, a European project, which is developing a system for the 3D dose imaging in case of low dose rate and high dose rate conditions, that is based on the innovative optical fiber dosimeters, which has on top, on the tip, inorganic scintillators. The system is using 16 of these novel sensors, which are coupled with SIPM, and the poster is showing how it is possible to make a source localization by opportune triangulation of information coming from the different sensors. Then there is this contribution, which is coming from frontier environment. So the idea is to develop and improve biological risk assessment of about the exposure of ionizing irradiation for to get better data helping exploratory space missions. The idea is that in the near future we will have a strong increase in the exploration of beyond low Earth orbit space, and so it will be needed to have a detailed description of a space radiation field. So the idea is to use information coming from many astroparticle experiments which are aimed at investigating the unknown universe components to fill this gap. So this is a research topic initiative that has been launched in November, last November, but it is still open for submission. Coming now to implant technologies, we have only one but very interesting contribution, which is coming from the SPEye collaboration. Here the idea is to use Silicon PhotoMultipliers to perform visual prosthesis, and so to face the big problem of the retinal degenerative disease that is hitting, unfortunately, 1 over 4,000 people in the world. The idea is that this disease can be cured by implanting SPEye arrays, which should be able to stimulate directly the healthy part of the retina, and then in conjunction, making a conjunction with the optical nerve. Obviously, the issues are many in this kind of project, which is quite interesting, and you will find information about, as an example, biocompatibility of SPEye with and the response to light and low intensity, and many other issues. I will then go to the last class of development of instrumentation then to improve imaging. This idea of fast timing with micro pattern gas detector for a time of flight PET, which is brought by Filippo Enrico and the colleagues, which is very interesting. The idea is to apply MPDG as that has a very good spatial and time resolution and affordable costs, okay, making it suitable for a full body scanner. We have now another contribution on the same research field, which is the idea to use, let's say, coming back to BGO as the preferred scintillating material in PET application by boosting this material with an artificial intelligence decoding algorithm in such a way that this material can comply with the time of flight speed requirements and so be aligned with LISO material. This is the last contribution of this section, which is a characterization of a scintillating fibre-based hodoscope. The kind of device which is based on 64 scintillating fibers has been developed for a different, let's say, aim, but it proved to be very interesting also for radiation monitoring in proton therapy, so we included in this life science section, and the calibration at the CNAO synchrotron has been performed, and the results are shown in the paper. I have now the last of our posters, which is the characterization of a charge sharing in multiple counts analysis. The idea is to use a detection system based with a high-Z crystal sensor, and the problems of this system is that they are often affected by simultaneous detection of a single interaction photon by different pixels, and the poster shows how to cure this issue. I come to the end, and I leave to my colleague to the second group.
And then we have the societal challenges, yeah. So which are also quite important in this specific time of the history. So how nuclear and particle physics technologies are spinning to the benefit of the society. And here we identified you will identify when you will go to the poster section, 5 areas. Homeland security, of course, and then environmental sustainability and cultural heritage, novel science divulgation, and instrumentation on the crossroads between nuclear and applied physics, and even a little bit beyond. Let me go very fast through the 9 posters, and of course you will be invited to go there and speak directly with the people. In this specific work, it's a new method for the material verification and nuclear security has been developed, and not only developed, also industrialized. So a commercial product has been done where innovative scintillators coupled to digital electronics with pulse shape processing is able to measure both gamma and fast neutrons. In this other work, the Urania detector is a detector used in particular for neutron detection. Also, you see here typical detectors used conventionally also in particle physics. In particle physics experiments are here used, so the micro airwell detectors are here used to detect neutrons and has been already the detectors have been already tested. The results of the test you will also find in the poster. A little bit close to that, close to different detector approaches, you will find gamma cameras. So here, the SIPM readout is, of course, now widely used because of the compactness of the detectors. The gamma camera is using mainly Compton scattering in order to detect gamma rays. Reconstructed images are already available. That's the detector assembly where you see the row of scintillators read out by SIPMs. Here from the simulation you see the readout. The readout, I suppose, is on the other side of the detector. Muon tomography. The second speaker today has mentioned the muon radiography. However, we have also posters on muon tomography. So glacier monitoring is, of course, important, in particular for climate change problems. And in this particular application, the detector, a detector has been done in order to monitor the thickness of the glaciers, and so indirectly measure the effect of global warming using specific muon detectors. So key point here is the compact SIPM readout, which is, of course, sort of a, in this moment is sort of a, in common with many detector construction and applications. So here we touch another important problem, which is imaging with neutrons. Of course, when we speak about neutrons, collimators play an essential role because of how neutrons interact with matter. And so what has been developed here is a compact neutron collimator in order to produce with neuron tomography. And here you see a nice example of tomography of a iron fibula. So you see the image quality and the precision of it is quite impressive. The muons fluxes, so muons are interesting not only because they're very simple, right, but also because they can help us explaining a lot and even communicate to younger future scientists what they're going to do when they will come to our universities. And that is what happens here. So the Cosmic Ray Cube is a portable tracking device conceived for outreach activities, and in particular also for your teaching, and in particular to motivate students from high school and above. So the detector is used to measure the differential flux of muons inside, and what is nice, you can see muons going through. Actually, if you've ever been in DAISY we had a cloud chamber where you could really see the muons going through. This is the modern version of it, yeah. So, and this is completely portable. The qualification of new companies. Of course, in applied research, when you are going to produce things, you need also to be sure that the quality is okay. And this is all about this poster. So this poster is showing how to qualify new companies for the production of resistive plate chambers in particular. So the team here developed a complete successful functional test, which is going to be used to assess the quality of all this, of the plate center. And finally, new materials. not finally, sorry, there is one more. So new materials. So GEM microstructures, so gas electron multipliers, of course, have still an important issue of the multiplication inside. And so new materials have been studied in particular in order to remove outgassing or lower outgassing, low coefficient for the thermal expansion, the dielectric properties, and of course, as told, the high amplification, which is a key point when you like to use these devices for tracking, for instance. And finally, muons again, used for beam monitoring. The scientists here from PSI developed a new beam monitoring detectors for high-intensity muon beam. Here, muons produced along the beam lines are used to detect a muon beam, and the key parameter here is the intensity, as the intensity is quite high. So the technology, completely non-invasive, operating in vacuum under high magnetic field conditions, which is the condition in the beam line, so it could perform particle ID. PSI is presenting here also how well the particle ID works with these nice detectors. So that's it. I invite all of you then, and I hope the poster people are happy about how we try to sell their science, and now we invite all of you later on to go and watch the poster session. So thank you very much, and I think we go to, yeah.
Yes, now we will have very soon the industrial roundtable. And so we ask you to wait just a few minutes, but stay with us so that we can put the installation that is needed. And then this new session will be chaired by Maria Giuseppina Bisogni.
I pray our industrial sponsor to come here and approach table. Sì, sì. Mancano 2 persone. Ok, iniziamo. Good afternoon, everybody, and thank you for attending this Industries Roundtable. First of all, let me thank our exhibitors for supporting this edition of the PISA Meeting on Advanced Detectors. Thank you again. And also thank you for attending and participating to this roundtable. Today we are going to know better the companies, their missions, their plans, and also opportunities they can offer to young people that is attending the meeting. Our hope is to stimulate further discussions with them, and then to identify possible collaborations among research institutions and industrial partners in order to face challenges of future experiment that we are in front of us. So thank you, and let's start with a short presentation of each company. And the first one is Jacopo Givoletti from Caen. Please come here, and there is a slide that you prepare. Thank you.
In
5 minutes.
Okay, so good morning everybody. My name is Jacopo Givoletti, and I represent Cayenne. So the company was founded in 1979 by my father, who was a former technician of the Italian Institute of Nuclear Physics. And during the years, the company has been growing and developing mainly electronics for physics research and basic scientific research. During the year, the company diversified in many areas and spin-offs. Some of those are not part of the company anymore, like aerospace and microelectronics. And today, the company is still the nuclear is the main entity in our company, and we have also other entities. Well, one is 3 companies like RFID, CNAO, and QS. The CNAO was a spin-off some years ago, but then we realized that it was better if it was inside of the mother company. The overall group is 170 people. We have been growing quite a lot in the past years. Just to give you an idea, CNAO designs radiation monitoring devices. RFID designs readers and antennas and tags for UHF RFID, so it's more in an industrial market. CNAO designs power supplies and electronics for magnets used in free electron lasers and synchrotrons, but they also find some very interesting application in more industrialized area, like the battery testing for electrical vehicles. So it's an area where the company is growing a lot. QS is just quantum security. They are specializing, they are consultants for IT security. So coming back to the mother company, where everything was born from, these are the areas where we work. So we design and realize power supplies and the data acquisition electronics for basic scientific research in the field of physics. Which field? Essentially all of them, from high energy physics, astrophysics, and nuclear physics, medical imaging, some industrial application, homeland security, of course, spectroscopy, gamma and neutron spectroscopy, and so on. So you name one of the applications, and we have something that we are providing, we are designing for. Coming back to the topic of today's presentation, technology innovation search. So what are we looking for? Of course, a company like ours must innovate all the time. So there is no rest for us. So it's where do we look for innovation? We look inside by our designers, but we are not shy to open our doors to whoever has some innovative ideas. And today I would say that some special ASICs are of our interest. Algorithms for gamma and spectroscopy and then gamma neutron discrimination. Detectors, why not? It is something that we are integrating quite a lot in our radiation monitoring devices. So if some of you has some interesting novel detector, we are always open to evaluate it. Power supplies, yes, why not? It is a field where it's a commodity, I would say, in the world, but if there is some interesting innovation, we are open to discuss. And about the personnel search, which are the people that we are looking nowadays. One above all is software engineers. It looks like that there are not enough software engineers. We are facing the competition of huge corporations that perhaps they have their headquarters in Ireland, and from there they leave people working from home in all countries, and it's quite hard for us to match their salaries. So I'm going to be totally open. This is a problem for us, and it's not only our problem, it's a problem of many Italian companies and many European companies. But if someone does not want to be just a number in a huge corporation and want to work with hands-on hardware or electronics and have more a human relationship in a company that's still a family-owned one, they are welcome. Physicists with software capabilities, they are extremely valuable for us because, okay, we design software, but having someone who has expertise and understand which are the needs of the physicists who are our clients, can understand exactly how to implement the best softwares, field application physicists, and electronic designers. So these are the main characteristics of the people that we are looking right now. And that's it. Thank you very much.
Thank you, Jacopo. Thank you for your presentation. And now we invite Elena Giglio from The Orbit.
Yeah. So first of all, thank you very much for inviting us to this conference. Actually, I'm going to be really fast because I know that you are waiting for the coffee. So the idea, and you are almost sleeping, so luckily the lights, it's not that by the way, so who we are, The Orbit, it's a space transport and logistic company that has its own headquarters in Fino Bornasco, that it's nearby the Como Lakes. And actually what we do, we usually used to call us the Uber of the space. It means we bring the technology into the orbit, in orbit, so technology and research, whenever the clients wants and whenever they needs, actually. So which kind of technology and research? As you can imagine, there are implications in many sectors. So we are talking about telecommunication, about Earth observation and climate change, and we saw the posters even before that could be actually interested in that sector. The agriculture enhancement, so let's think, for example, precision agricultures. And then oil and gas industry, forest management, autonomous driving, and much more. So all those sectors could be really interested in using our technology to overcome one of the most important gaps that also European Commissions face at, I would say, at world level. So the fact that most of the technology and most of the research fail in the demonstrations and validations theory. So this means that whenever you could also have one of the most important technology, but if you are not able to prove that it's valid and it's marketable, you are going to fail. So that's the point. So what we do actually, it's help you in reaching, it's in the go-to-market, let's say, so in reaching the market as faster as possible. And when I say as faster as possible, I'm telling you the truth, because let's forget the normal time of the old space market. We are, I can tell you that through the technology of the new space sector, we are able to bring you into the orbit, so demonstrate and validate the technology in a total of 8 months. So that's a lot for a technology and for a research. And that slide, it's important. I didn't mention anything, but it's important. Why? Because just as I know that most of you are PhDs, So, for example, the European Commission just launched the Marie Curie Slodowska Actions, that are the European Global Fellowships. So maybe you could be also interested in apply for those researchers. And those vacancy actually totally paid by the European Commission with a very good salary, by the way, foreseen also a mandatory time to be spent in a company. So whenever in our company, but even in other entities, you could be interested in applying and present a project like this one. And this is useful not just for the researchers, for the single researchers, but of course also for the research teams. We are talking about universities and department as a general, in a general view. So, as already said, what we do, it's the implications of our ion technology, so in orbit now platform, that it's this carrier that we use for the technology demonstrations, has an implication on to move the TRL, so for the technology demonstrations, an implication in science, and we saw again many posters that could be related to that objects. Earth observation and remote sensing. I don't know if, as we had only a few slides, I don't know if there is a slides, but one example that I want to give you is the fact that, for example, we tested, it was last year, a telescope from the Astrophysics Institute of Canary Island. It was a demonstration technologies, so it was supposed to be a technology that still have to be demonstrated in orbit, but in the meantime, there was the volcano eruption in the Canary Island, and that technology has been used also in an operative way from the government and from the islands. So that was actually an additional added value for the institute. So that is the career that we use, and that is the platform in which we actually put the technology, either the research. Whenever you need further information, because I know that we don't have enough time, just come to our booth. Then maybe it's the poorer one, but we are in the meantime in the same week, actually like 4 or 5 conference in the same moment, so it was even difficult to arrange the booth. But please come to us and ask whatever information you need from us. And the added value, which is that it's simple. We foreseen actual frequent launch opportunities. We have done in less than 2 months 6 missions that are actually operated in orbit. So we could say that we have every Tajan flight. Then we are affordable also in terms of cost, because it's cheaper, much more than what you think actually about this kind of technologies. We are customized because we somehow respect what the clients need. Let's think about the orbit and so on. And we support the advancement, as already said, in technology and research. So that's all, I guess, that I don't have any other slides. So thank you very much, and whenever you need, at the booth outside. Thank you.
Thank you, Elena. Working. Maurizio Boscardin from FPK.
Okay, good afternoon. So I am present. I work in Fondazione Bruno Kessler. Okay, Fondazione Bruno Kessler is a private foundation, but yeah, strange respect to have colleague, because you have some way public and some way private. We are located in Trento, north part of Italy. VPK is composed by a lot of different centers for different topics. We are working in Silicon Device Center. And so Silicon Device Center has a focus, the activity on develop and realization of device in hydrophysics application detector, MEMS, or photonics, and now we are involved in quantum technology. Our capability is based on a clean room. We have now 2 clean rooms, one focus on detector for high quality, low contamination. Another clean room is focused on MEMS. so more flexible. We also have a testing area in order to have a fully characterization of the device from an electrical point of view. And an integration area we are developing in order to have a small capability now, but to increase our capability to mount a device with front-end electronics or some mechanical part. And the last lab that now we are in progress to build is to have capability to have a 3D integration based on 2 silicon vias, but we explain. So we have internal capability to realize a device, starting from scratch, simulation, layout, and the fabrication completed internal and analytical characterization. Sorry. Regarding the silicon radiation detector, we are a group of 25 people that work on this activity. And we are developing inside silicon PM for different kind of application, silicon drift. Now you work a lot on silicon drift, maybe for X-ray and for a synchrotron and for space application. Work on silicon strip and pixel. For example, now we are involved in fabrication of Atlas pixel for ITK. Low-gain avalanche diode, we have a lot of activity on low-gain avalanche diode, and also we work on silicon 3D, and also on silicon 3D now we are involved in production for Atlas ITK. The application is mainly different in science application, but also we have some collaboration, working partnership with industrial partner to have some, to develop, to realize device. We are able to make some R&D activity, but also we have the internal capability to small, medium production. Finally, the last is focused on IPCEI, which is a European program that we are involved with. We have inside a lot of industrial partners with big capability on microelectronics in order to increase our capability into silicon vias. So we are hope in some years, 2 years from now, to have internal capability to thinning, make hole, filling with conductive, isolation, and in order to have a bond bonding between different technology. The last slide is only for young people, okay? We have checked on this site. Sometimes we open some position, and if you are interested to work inside FBK, maybe it could be a good possibility to have a good experience, direct contact with production, development, and the development of new device. Okay, thank you.
Thank you, Maurizio. Alexander Pellicone from Galli & Morelli.
Okay, good evening. My name is Alexander Pellicone. I'm a vice president of Galli & Morelli, a precision mechanical workshop in Lucca. Our company was founded in 1982. We specialize in construction of machines for paper and cardboard production, and in the construction of special equipment operating in high vacuum condition. For over the 30 years, we have been collaborating with many research institutes and the university in the design and the production of experimental equipment for research in fundamental physics. In this context, we have built the complex mechanical system to isolate the optical element from the seismic noise in Virgo and advanced Virgo. And thanks to this experience, we also built similar equipment for LIGO, TAMA, and CAGRA experiment. We have worked also for other important projects like KM3Net project and Xenon NT project. Our services were able to manage all the phases of the production process step by step, starting with the materials acquisition up to the final test of each mechanical element, those requiring the clean room for assembly. We were able to machine different materials, also the high-tech materials, and also now we are working in an important experiment like KM3Net experiment, the upgrade of LNS superconducting cyclotron, and also for ET Pathfinder project. Now we are investing in a high precision machine tool, and we are always looking for young people who wish to work as a CNC operator, but it's very, very difficult to find young people and skilled and unskilled worker. This is for us is a very big problem. Thank you.
Thank you. Now I invite to speak Simona Ferrulli from Hamamatsu Photonics, Italia.
Good afternoon, everybody. My name is Simona Ferrulli. I am sales engineer in Hamamatsu, Italy. Let me start to present our company. Hamamatsu was founded in 1953 in Japan, and today boasts over 5,000 employees in the world, and a net revenue worth $1.3 billion. As a company policy, we invest around 9% in research and development, leading us to a contribution to 3 Nobel Prizes. Today, starting from headquarters in Hamamatsu City in Japan, we have expanded to enjoy a global presence in the world with the business office, and today we have 7 manufacturing facilities in Japan and 3 central research laboratories. Here, presence in the multitude of market, our photonics solution are found in different applications, such as food, automotive, medical, analytic labs, and also academic research and life science research. From component to the modules, our capabilities include optics, electronics, software, and mechanics. Today, our photonics detectors covers a broad spectral range, and we develop high sensitive detector and customizable modules. Systems, cameras, and so on. This slide shows you 3 examples of regarding the high energy physics field. This slide shows you 3 examples of the most important experiment in the world. For example, that we provided our MPPC. For example, in 28, we provided around 60,000 MPPC for T2K experiment or also other example is MEG2 experiment, and in 2018 we developed MPPC array for LHCb fiber tracker. Here show you other 3 examples of experiment in which our MPP and PMT are involved. In general, PMT is used with water, ice, or liquid scintillator to detect Cherenkov light. For example, superchemiconda is a very famous related to that in Japan got a Nobel Prize. Finally, the last slide, I will show you what our local office consists of. Sales and support team are skillful and talent, with over 88% doctors and engineers. We provide technical solution to any queries. We have also a demo room in our office in Milan, where the customer who wish to perform with our product. And thank you very much.
Thank you, Simona. Now is the turn of Lilith of Hilger Crystals.
Good afternoon, everybody. My name's Lee Lyth, and I'm the Business Development Manager with Hilger Crystals. Those of you who perhaps are not familiar with Hilger, we're a UK-based company, and we've been growing single crystal synthetic crystals for over 70 years. Originally, this was to provide quality optics to the Hilger instrument business, which was created in 1874. So I think we win the prize of being the oldest company. We currently produce synthetic crystals for optics and also X-ray imaging and detector assemblies. We are a manufacturing company, and as such, we comply to many ISO standards for the ISO 9001 for quality, 14001 and 45001 for health and safety and environmental legislation as well. We work closely with our customers. We're a fairly small company, and we provide bespoke solutions to those customers. And as such, we can have full product traceability from start to finish, from raw materials to final products that leave the door. Arrays we produce as linear or two-dimensional arrays. These are custom built to customer requirements. Detector assemblies, again, these are all custom built. And we work with individuals from universities, PhD students, through to full OEM companies. And in that respect, we're providing maybe 1 or 2 arrays, up to thousands of arrays per month to some of these companies. Here is just a brief list of some of the materials we produce. On the left is the optical crystals. These are the salts normally for infrared spectroscopy. And the right is an ever-increasing list of scintillation crystals. These are some of the most common ones we supply and process at the moment, but it's not an endless list. We are actually part of a bigger family of companies, the Dynasteel Group, which is a USA company that comprises of Dynasteel Fused Silica, ourselves, and as many of you may know, a company called RMD, or Radiation Monitoring Devices. They're a fundamental company in research, and I'm sure anybody who knows RMD would have known Kanai Shah, who headed up RMD, who unfortunately passed away in March this year, and he will be greatly missed by everybody. Key applications for the company, homeland security, and we do baggage scanning, cargo scanning, parcel scanning, medical imaging, we do PET scanners, detectors for PET scanners, and we have a whole range of detectors for geological applications, for hospitals, for steelworks. It's a broad range of applications that we can provide our products to. We work closely with academia, and we'd like to introduce our company to those of you who have not met us before. Moving forwards, we're now entering into an exciting era for us. We're just about to embark on a brand new facility, not only to expand our production capability, but to also expand the product capability. We hope to fairly quickly get up to speed with our new products, which will include high pressure, high temperature scintillation crystals, and also some HIP processing or hot isostatically pressed crystals, which are ceramic to most people. So hopefully this will be up and running within the next 12 to 18 months, and this will provide many opportunities both in marketing and development. Thank you very much.
Thank you. Next speaker is Amanda Boothby from Micron Semiconductor.
Hello. Hello, I'm Amanda Boothby. I'm one of the directors of Micron Semiconductor Limited. We're based in Lancing in Sussex, which is an hour south of London. We also have just set up a sales office in Paris to help with Brexit since that occurred. We are 80% export, but we tend to specialize in custom detectors and work very closely with scientists, and we tend to have a sort of niche market position in the world. Oh, I think I pressed something wrong. Sorry. Our main focus is the silicon detectors. We've been making silicon detectors now for 30 years, and we focus on the P and N type, single and double-sided, particularly double-sided, quite complex detectors. And we have a very good design manager, Dr. Suzanne Walsh, who works with the scientists and produces the different shapes to best suit your equipment. We often provide just one or two detectors rather than the high volume capabilities. We can also offer AC and DC coupling and thickness range. It says from 10 micron to 2.5 millimeters, but we're also offering much thinner now. I think we're down to 5 micron. Recently, it's about 3 years ago now, we set up a diamond arm, and we have been developing our diamond detector market. We supply a lot to China. We luckily got to visit China just before the pandemic and met with lots of scientists. And Dr. Gwenny Lefebvre is my diamond research manager, and she explains the capabilities of diamond, and we've won some quite lovely orders in China. And we have a good agent there that helps market this product. As I said, Suzanne, design is integral to what the detectors we can offer. We do have a large catalogue nowadays which shows the various detectors we can offer, but often the customer comes to us and wants a change. They always want something slightly different, and that's what Suzanne works with. But it's good. It's what we like to do. And yeah, we offer different sizes, different packages depending on what you need. Ceramic, PCB, and we have a very good relationship with our PCB suppliers. Luckily, we've not really hit too many problems with our supplier chain, despite the worldwide difficulties. just to show you a few of our applications. We're quite well diversified, so we offer obviously the nuclear physics, but we have some strong space customers. We work very closely with NASA. We have a lot of American customers. We work very closely with NASA and have done the space weather satellites and also, as you know, more familiar projects with yourselves and LHCb and things. Our OEM market is also there. We're also developing that now with the diamond detectors, which is sort of the OEM market is our probably more simple detectors that we sell quite a lot of each month, alongside the more complex nuclear physics and space orders. And we're now beginning to offer this in diamond as well as silicon. We often sponsor students through university collaborations. We're working currently with the University of Surrey with our diamond detectors, and Queen Mary in London. We've just I don't know if anyone from Queen Mary's here. They've been working on a curved detector, which is ready now. Oh, have I gone on? Sorry. And we link in with Ken and University of Liverpool with our student sponsorships and case. We offer case studies. We also are hiring at the moment. We want sort of young testing engineers, short-term contracts really, because the orders ebb and flow. So sometimes we have orders where we need a lot of testing, and we welcome young students to come and spend some time at Micron. And we are developing, we have the R&D is also a strong area for us, and so we are looking at perhaps hiring somebody that has interest in the diamond detectors and also silicon carbide. That's it.
Thank you, Amanda. And the last speaker is Paul Skotanus from Xionics.
Hello, I'm Paul Schotanus, Managing Director of Xionics Holland. We are a Dutch company that manufactures and designs scintillation sensors. Sensors to be used, as you all know, in medicine, industry, science, security. The number of applications is really numerous, and the number of possibilities to design scintillation sensors is also very extensive. We use all commercially available scintillation materials to design our sensors. And all scintillation materials have different properties. So every time we have to talk to you, the users actually, how we best can propose a certain material for your particular application. At the moment we are concentrating actually on high resolution sensors like fast cerium bromide crystals and or lanthanum chromochloride materials. And we're trying to use materials to the best of their possibilities to see what we can get out of it, that it really suits the application. We use for light readout, we use of course classical photomultiplier tubes, but the last years we are concentrating a lot on silicon photomultipliers, of course. Silicon photomultipliers that offer a lot of possibilities and advantages to classical photomultiplier tubes. We shouldn't forget, however, that also these toys have their limitations. Especially when we're talking about larger volumes, when we want to read out kilos of scintillation material, we need quite a lot of SIPMs, and these things are rather noisy. So people who say that the photomultiplier tube will totally disappear, I don't totally agree with. But there are very many applications in industry, for example, or in medical applications, where silicon PMs have a great advantage, that they operate at low voltages, are compact, insensitive to magnetic fields, for example. And you see here a number of our sensors that contain silicon PMs used for gamma ray detection, alpha, beta detection, and just ask us if you have a specific application and you think SIPMs may be an option for you. So there's a new generation of scintillation sensors these days operating with silicon PMs. We can do neutron gamma discrimination with these devices, as you see here in the left curve. I'm reading out a liquid scintillator with SIPMs. So we are a company that is very general use active in the field of scintillation sensors. But we need input from you, what you want to achieve for your experiments. So we can assist you and advise you what is the best option actually for your problem. Thank you.
Thank you very much from the speaker. And now the roundtable is open for discussion. If you have questions for our speakers or comments, please, one question or comment.
Yes, let me say that I'm delighted to see such an array of companies at this conference working on the bleeding edge of technology, so I'm really grateful that you made it here. And I think that one point I wanted to raise is the issue of, that's the title of the session, which is the societal impact of our research. I think that for us, you are making, you are the ones that are making our dreams real or possible just by developing the technology, but also these things have a big impact for society. And many of the things you do are not related to physics, but actually have a big impact on the society. And I think we have to be more proactive and maybe do a better work in making this evident, because that will help us to get funds and help you, to develop your products, and also give us more access to a lot of opportunities that are now available. I'm thinking in Italy of the PNRR, but also I think in Europe in general, there are a lot of opportunities. So it's not a question, it's more like a general comment, but if you have some wisdom to add to this, I think it would be most welcome.
If you want to discuss about this point raised by Francesco, okay, you can use this microphone, yeah? Sorry?
Well, is it working? Yes. Francesco, you're right. The results of the physics research is used in applications that are of daily use and many times is not even seen. Just to give you an idea, some of our systems, our radiation monitoring systems are used for homeland security applications. We delivered some instruments to the special forces of Marina Militare, the Italian Navy, and they are doing special operations on cargo inspections, just to give you an example. And this is not something that we are advertising too much, because we work in the field of basic scientific research, but this is a clear application of that. Another application is the commissioning and dismantling of nuclear waste. This is, we are project leaders of the Mikado project. Is a huge project for doing the digitization of nuclear waste. Another example, we are providing instruments to inspectors of the International Atomic Energy Agency when they are doing the inspections on nuclear sites. And this is, again, this is something that has a very big impact.
Yeah, just one point from my side. I guess that one of the main problems we still have is a communication gap. I'm talking especially as follow-up of my previous jobs as national contact point in Italy for Horizon 2020. And I still can see that many researchers don't know what are the opportunities offered by the huge advancement of the technology we have worldwide, actually. And let's think about the technology that E-orbit has. It's really cheap. Researchers, I would ask to all of you, what do you think about how could cost, for example, a testing in orbit via our technology? I guess that most of you will say a cost really, really huge, more or less similar to the one used for the International Space Stations, but it's not that way. I mean, we are talking of a new space economy. We are talking of a technology that, for example, use automotive technologies, so they are cheaper, but this doesn't mean that the quality is low, actually. It's just cheaper and faster than in the past. And that is really needed for the researchers, because, as already said, there is a huge gaps in terms of TRL advancement. This is what makes the difference nowadays. So,
thank you. Other comments? If not, there is another question there from the audience.
Yes, I was wondering what is your perspective about how well we educate the people that you're hiring. Can you hear? Yeah.
It is.
Is it working? Yeah.
So are you finding I'm a professor at university. I was wondering if we are producing the people that you want at your company, and a couple of you said that you don't have enough people filling your position, and we actually have the same problems sometimes to replace engineers, etc. at the university. So I was wondering, are we doing enough or can we do better?
It's my opinion that the whole field of sensor technology is not enough in the picture at academia. Sensor technology is considered not really physics. You're doing physics where you want to, in the end, want to have a Nobel Prize for. Also, anyway, that's the ultimate. But sensor technology is considered engineering. And when in the academia there is not more knowledge around about sensors, we cannot, in the end, develop the instruments we need for society. So I'm a strong advocate of an increased educational program to teach students how sensors work. And sensors start analog. And at the moment, digital electronics is much more sexy and much more fashionable than analog electronics, but it starts all analog. So understanding a sensor is, I think, should be more attention in the educational whole process at the universities, actually worldwide.
I want to just say one thing. The average in our so the orbit has been funded in 2011, and now we are almost 200 people working for the company, and the average of the age of the people working for the company is 31. So actually, we are a really young company. I'm the oldest one, to be honest, one of the oldest one, and. We have brilliant, really brilliant, I have brilliant colleagues in the company, maybe, and I'm talking also as a recently PhD student, because I took a PhD student in the second part of my life, let's say, and I would recommend a better cooperation with the company, but not in terms of make the PhD as the slaves of the company, because PhD are not slaves, actually. I know that this could be a huge discussion, open discussions, but a better cooperations it's needed in order to let the students open to the positions that the company are looking for right now. Because even my company, we have actually right now almost 40 positions open, and we are struggling in finding, for example, software engineer or either system engineer as well. So it's a huge problem. But the cooperation between universities and company, it's a huge problem that have to be solved. And this is not a problem that we have in Italy, actually.
But Jacopo raised another problem that was the salary.
Yeah.
The competition.
Well, you know, imagine a young engineer that receives 2 offers, one from Kane and the other one from Apple or from Intel, you know. To the eyes of a young engineer, you know, a very renowned brand, it's you know, is a no-brain decision. I go to Apple because it will, you know, feel in my resume, you know, it will be a huge reference for my future. But then these students will be working in you know, in compartments, because these huge corporations, perhaps they have very strong rules for intellectual property defense. And they will see perhaps a small part of a huge program. In our company, they will see, you know, everything. You know, they will see the wall, and they will understand the project from the beginning to the end. Salary, yes, it is a problem, because if Apple is hiring in Italy, but the headquarters is in Ireland or in Luxembourg, which are fiscal paradise, how can you compete? It is totally unfair. I would, you know, if I have to tell you the truth, I would be happy to pay the same amount of money that I'm paying today, but if our state will reduce the taxation on the salaries, you know, in order to have more money in the pockets of the employee, and I am willing to pay the same amount of money, but this is what we have to deal with. And our situation, or the deorbit situation, is the same one. We are struggling to find people. There are simply not enough.
And actually, we have another problem. We have many people coming from abroad, actually, in our company. And what is happening is that in the same team, there are people coming from Netherlands, either UK, with a higher salary than people in Italy. And that's, I mean, in order, as we are in crisis to find software engineer and other profile, we need to pay much more for those profile coming abroad compared to people based in Italy, actually, for many reasons. So that is another huge problem in the same team, in the same company. So it's not easy.
Yes, and this will create, imbalances in between the people, because colleagues, they compare the salaries, and it is just a huge mess.
It's fine. So, just a few words. First of all, I'd like to remind that in the past years, I had interactions, at least with 4 of your companies. And all these kind of interactions were very positive, I should say. And the right format was not that we were simply customers buying things ready on the shelf. We had real interaction, okay? Sometimes for a long time. And that was I think, the right format of interacting with the company from the academic side and from the research side. Concerning the problem of people and bright people to be hired by you, this is a serious problem. Nonetheless, I must remind that some of my students have been hired from one of these companies. And I think with success on both sides. Unfortunately, there is a problem of salary. It's different to live in the Silicon Valley or living in this country, actually not only in Europe, but in Italy. I think we should do whatever we can.
Thank you. I think that we can move to another question, or this.
My question has already been addressed.
Okay. So any other comment from? Okay, so Angelo.
So let me recall briefly. 1992 was the second PIsa meeting. If I remember correct, it was in Castiglione. It was the first time that we invited exhibitors, industries, of course, of our sector. Okay. Somebody was, thinking that the idea to have exhibitors, was between sellers and buyers, as Marcello said. But the idea was another one, was to meet users and producers, but to collaborate and to stimulate the collaboration in the future. Somebody was thinking, no, exhibitors are just, they come just to help PIsa meeting, financial. It's not that, okay, of course. So, but if I remember correct, this is the first time that I see industries, representatives of industries in a table, in front of our colleagues. Okay, so let me say thank you, first of all, to the organizing committee for the idea, okay, and then thank you to you for having accepted to stay there, to present your industries, and I hope that in the future this will be more collaborative, okay? Thank you, again, thank you.
Are there other questions, comments, also from our, one more? Where? There.
Thank you. Hi, I'm Daniel. So I make a comment from the young side, let's say, not based on my personal experience, but on colleagues which are at the same age and that did a career similar to the one I did. And one comment I would like to make you is that it is not only the salary what makes a difference when you go from one to another, but also, and that is something what I think, and from the experience of my colleague in which most of you can improve, is one is the flexibility, yeah, because money is not the only thing in which there is a competition, because if you are working in a different environment with a different flexibility, which in this moment allows you to do more remote working, for instance, or to work in different places, that is obviously a plus. And then also, judging from their experience, also in the moment in which you do the interviews, I think there is something which you can really improve. Because companies based in other countries maybe have a better ratio of response when you apply for a position, and the interviews themselves are often value better the career of the people that are applying, while sometimes in other companies, I'm talking in particular in experiences in Italy, they did not really look into what that person had done, but they are just maybe going into some logic test or something like that, and I think that is not the way to go. That was my comment from that side, and I think that is something that in which it's just about the change of mentality more than a matter of money or whatever.
Thank you very much for your comments. Do you want to reply to?
Well, in our case, for example, we started to work remotely before the COVID issues. So actually, for example, our companies, we don't have any badge. We work by objectives, and that is one of the reasons why I accepted to move to the orbit. So I don't have to stay in front of the computer from 9 to 6 p.m. because it's something that I really don't like. But of course, this means that often happens that at 11 p.m. I'm still in front of the computer. So it's depend. I mean, when you have to work remotely, there are good things and bad things. So life and way to work is totally different. And I can tell you that, especially in the new hires in the company, sometimes this is not well understood, because they love the fact that we don't have the badge, but then when you ask them that there is something to be finished, even late in the night, they are not that happy. So there is something that have to be better understood, but I agree with you that companies have to be somehow adapted in the new era, especially after the COVID pandemic.
So, no more questions or comments. Thank you very much for this interesting, of course, for your presentations, but also for this interesting discussion. I think that there are important take-home messages that we got from it. And thank you very much again for present here, and thank you for you all for your attendance. There is the coffee break now, where you session. Thank you very much again.